So now, we left off talking about the periodic table and the elements, just kind of did a quick introduction. Thanks. So now, what was the rule I told you about elements and how to use their symbols? If you use capital letter and then what? A lowercase letter. What happens if it's not a lowercase letter? It'll be something else. Could be a molecule, right? It's certainly not an element. Elements always have an uppercase letter first, and if there's a second letter, it's always lowercase. Always. Okay? So that's the rule. Now, let me just scroll back one slide and we can start picking off some different elements on the table. What I want you to do is I want you to get used to looking at the table, not necessarily memorize it, but some of the elements are so commonly used that you can't help but remember them. You see what I'm saying? For example, carbon is right here. Nitrogen, oxygen, sulfur. Those are the ones that you'll just remember because we're going to see them a lot because they're quite common. And I use them a lot because I'm an organic chemist and those are the elements we use. Ones like iron are quite commonly used. Fe is iron. So you'll get used to seeing them. I promise you though, I will give you a table, this one, better than this one actually, and it will have the names of the elements printed on it right underneath or above them. So you'll have the names at your disposal. Please do not even attempt to memorize this. Okay, so this question wants us to identify the element iodine. Iodine is right here, symbol I. That's a nice one. Why? Because it starts with an I and its symbol is I. That's a very nice element because it's easy to remember. Iodine is element I. Iron, that's a bad one. Well, not a bad one. It's just iron is Fe. At one point, iron was called ferrous or ferric. Now it's called iron, but the symbol still stays. It's Fe. So if you want to draw the symbol for iron, you don't draw IR. IR is a different element. Fe is iron. What else we got? Magnesium. Magnesium's way over here. That's magnesium. Mg. Kind of makes sense. Magnesium. M-A-G-M-G. Kind of makes sense, right? Zinc. Zinc's a good one. Zn or Zn. There it is. Zinc. And nitrogen's up here. So some of these elements are very simple because the letters and the names kind of go together. Some of them, like iron, are difficult. What is what? Zinc, Zn or Zn. It's right here. So that one kind of makes sense, right? Z and N make sense for zinc. But what about, well, here's tin. The element tin is Sn. The element lead is Pb. These come, I believe, from the Latin names from these elements because a lot of the elements have been around for over, well, hundreds of years. So they are named by ancient people and their symbols have stuck. They've just stayed with us, which is kind of neat, right? I mean, we're still, giving homage to history kind of thing. Now, you can also look at the symbol and pull out the name of the element. Now, your periodic table that you'll get on the exam will have the name of the element written clearly on it. No problem. But just kind of follow along with me. Element P. Most people who aren't familiar with chemistry want to say potassium because they've heard of that one, right? But it's not potassium. Potassium is over here. Potassium is symbol K. That's weird, but it's true. That's potassium. P is phosphorus. That's phosphorus right there. That is not potassium. That's phosphorus. What's the difference between potassium and phosphorus? Well, potassium, upon reaction with water, will blow up. Phosphorus, upon reaction with water, won't. Phosphorus, however, on contact with oxygen, will burn very brightly sometimes. Depends on the type of phosphorus you're using. Did you ever go to the store and get a book of matches, those safety ones that you strike and they light on fire? That red coating, that's phosphorus. And if you strike it, it catches on fire. Pretty neat, huh? Mn, there's a weird one. Manganese. Manganese is right there. H is hydrogen. Hydrogen's right up there. And potassium is right down here. Now again, don't memorize these. But some of them, honestly, you're just going to get to know them because you're going to use them a lot. It's just going to happen. So don't panic. You're going to learn a lot of them. And don't worry about memorizing it. I never require that, and I never will. Okay. The periodic table. This table that I've been referring to since last week is called a periodic table of the elements. Now, looking at this table for any element, I can give you a wealth of information just by knowing where it is on the table and all the information that's printed on it. For example, if I looked at the element gold, gold is AU, number 79, on the row number 6, right here, beside mercury. By looking at that, I can tell you the number of protons, the number of electrons, the mass, where the electrons are and how they're arranged. I can tell you all that just by knowing that gold, AU, is right there. And by the end of this class, well, not this class, but this lecture, this whole course, you'll be able to do that too. It's really simple once someone shows you how it's done. But now, while we're here, let's learn some basics of the periodic table. These 3 elements right here, I show these because they're the prettiest ones. They have a really nice color. The one on the left, far left, the yellow one, that's chlorine gas. The one in the middle, the red one or the orange one, that's bromine. Bromine's a liquid. But as you can see, there's a whole lot of vapor above the liquid. So it's a volatile liquid. And the purple one, that's iodine. Iodine is purple. And it gives you a purple vapor.
Is that what they put in salt?
Salt? Oh yeah, no, not the same kind of iodine, no. Well, when we get there, I'll point it out to you what they do. But very good for you. So this is iodine, bromine, and chlorine. Now, those elements are right here. Chlorine, bromine, iodine. Kind of neat, huh? So they go from gas, liquid, solid. They change phases right through here, which is kind of cool. Now, looking at this periodic table, the red ones, the red elements, these are gases. So all the red elements are gases. The blue elements, there's only a few of them, are liquids. So mercury and bromine are liquids at room temperature. And iodine, the black elements, are solids. Kind of cool, huh? Excuse me. I woke up this morning with a slight fever, so if I'm acting a little weird, call the hospital. All right, the periodic table. Now, this is how we arrange the table into groups and periods. Write that down, groups and periods. Every periodic table in the world is arranged this way, groups and periods. Groups run top to bottom. Periods run left to right. So now if I'm looking at this table here, and I said, point out a group, well, this here could be a group. That's a group. So is this. So is this. Top to bottom, those are groups. Left to right, that's a period. So now, looking here, this right here is group 1. This is group 2. This is period 2 right here. Runs all the way across here. So that's period 2. Up here, helium and hydrogen way over here, that's period 1. Now, for now, we're just going to talk about that's how it's arranged. When we get to electrons, I'm going to show you how the periodic table tells you where the electrons are, or gives you an idea where they should be, is what I probably should say. All right, so rows and feverish, groups and periods. Okay, groups top to bottom, periods left to right. No problem, right? Let's point that out right quick. This table here, looking at the red numbers on top. So these ones here, everyone see where I'm pointing? Those are the group numbers. Now, right here you can see that this is group 2. Beryllium, magnesium, calcium, all the way down. Also, there's that 2A. That is a different way of looking at a table. That's the older way. I, being a modern person, don't like the old-fashioned way. I don't like this way. So I don't use it ever. Now in the book, you'll see it. So I want to make you familiar with what it means. Group 2 is group 2A. It's the same thing. These elements down in here are the B group elements. And then the A group picks back up over here. Very confusing system, in my opinion. So I never use it. What I use is this system here on this table. See how it's numbered 1 through 18? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I use that system. I think it's an easier system to use besides the AB system. Okay, so if you see the AB system in the group, don't fret. I'm never going to use it on exams. And the book, I believe, uses both to help you along. I don't know why people still use that old system, but they do. Okay. Don't worry about this. Now, write this stuff down. I'm going to write it on the board for you. Group 1. Those are the alkali metals. Group 1 are the alkali metals. Now the word alkali means basic or base-inducing. So they're the alkali metals. Group 2 are the alkaline earth metals. So group 1 are known as the alkali metals. Group 2 are known as the alkaline earth metals. So if someone says on an exam and a multiple choice question, group 1 elements are also called the, phosphorus, Larry, representative elements, or alkali metals, you would say they're alkali metals. That's the other name for them. Group 3, so the middle ones, through group 12, so this gray area right here. This whole gray area. On this periodic table, it's right here. So there's that little cutout right up top here. Everything down in here. All these metals right in here. Those are called the transition metals. So those are called transition metals. I know, it gets more exciting later, I promise. All right, so group 13 through 16, they have no real common name. So group 13 through 16, no common name. So there's really, there's no cool name for group 13. There's just not. I wish there was. It'd be kind of neat, right? I would call group 13 awesome. The awesome elements. Group 14 would be the very awesome elements. Group 15 would be the totally cool elements.
Is the bottom included?
What's that?
58 and 59, are they included?
The bottom ones, those are called lanthanides and actinides. They're very different, but what they actually should be, they should be right here. So see this element here, 57, and this element here, 72. This whole row here should be right between these two. There's a reason why they're down here. We'll get into a little bit later, but in this group, we very rarely talk about them in this class. In fact, I do organic chemistry for a living. We never really talk about these. Every now and then you'll hear us talk about them, but very rarely. Most of these elements, as you can see, are ghosts. The ghost elements are radioactive. So they're either synthetically made and very unstable, or they're natural but very unstable. And which is probably why most people don't use them, because they're dangerous. It's a great question, though. All right, which leads me to group 17. Group 17 has a pretty cool name. Those are the halogens. Halogens. So chlorine, bromine, iodine, fluorine, they're all halogens. And the last ones are the noble gases. Group 18 are the noble gases. Now, let's talk a little bit about group 18. Group 18 are noble gases. The word noble carries a lot of weight. Nobles were, back in the day, if you're going to have a ringtone, have something cool that we can dance to. Maybe a little club music. We can all, So, anyway. Okay.
Professor,
Yeah.
I'd like to ask a question. You said that it's back to the periodic table. You
Yep.
said the black elements are solid.
Yes, they're solids at room temperature.
And the blue one are?
Liquids at room temperature.
And the other one is gas?
Are gases. The red ones are gases.
Okay.
The ghosts, the ones that are ghosted out, those are radioactive.
Okay.
Or, I believe it means they're radioactive. Or they're synthetic, one or the other. Probably both.
Yeah.
Okay. So now the noble gases, the word noble carries a lot of weight. If you were a noble man, you were really doing well back in the day. You were respected, you had money, you had land, you had tenants, you had people that paid homage to you, you had a lot of money. So people like scientists like me, who had to work, or worked a lot, probably didn't like the nobles very much, because they didn't do anything, right? Nobles usually don't do much, besides collect money and drink champagne or whatnot. So the noble gases are unreactive. They actually don't do much. They don't do anything, actually. A lot of them are inert. They are chemically inert. Now, can you make them react? Sure, you can make them react. Like xenon, you can force it to react. Very unstable. So the noble gases are unreactive. So there must be something special about being a noble gas. And when we get to it, I want you to remember that. There's something special about noble gases. And it's not a coincidence that they're at the end of the table. They're at the very far right-hand side of the table. That's by nature and by design. The person who designed the table, Mendeleev, designed the table to put those elements at the end. And there's a reason why they're at the end. And there's a reason why they're not reactive. But we'll get to it soon enough. Group 1, these are your group 1 metals. Now this is lithium, potassium, and sodium. They are, notice the person using it is picking them up with forceps or tweezers. There's a reason for that. This stuff is very reactive in water. If you feel your hands are probably somewhat clammy or wet. So if you touch it with your hands, it'll react with your water in your hands. Now it's probably not going to blow up in your hand, not enough water, but it certainly eventually will burn you. Excuse me. And I think I told this group last week to go and Google that on YouTube, right? Oh, yeah. The group 1 metals in water. Did y'all do that? Anybody do that? You're missing a great show. So go Google group 1 metals in water and see the fun. Especially when you get down to the larger ones like cesium. It's kind of cool what they do. And it's real. It's not a made-up video. It's real. These are your halogens. I already introduced them to you. Chlorine, bromine, and iodine. Those are your 3 main halogens. Fluorine is also a halogen. A very reactive gas. So these things, such as chlorine, someone already asked about iodine and salt, these things do play a role in our life. Sodium, of course, everyone knows that. Sodium plays a huge role in our life. And so does chlorine. You need them both. All right, write this down for me, please. Metals, nonmetals, and metalloids. Just write it down and we'll look at the table and I'll point it out to you. Metals are on the left-hand side of the table. So everything on the left-hand side of the table is a metal. Nonmetals are on the right. And metalloids are kind of in the in-between zone. Now, I don't know if all you guys can see it. It might be a little bit faint for you guys in the back. There's a line that runs right here. It's a red line. Someone drew it in. Can you guys in the back see that? That red line right through here? Everybody? Yes. You guys can't see it? Can you guys see it over here? No? Let me draw it. Don't tell anyone this. I never did this. Probably get in trouble or something. Draw it in blue maybe. How's that? Is that better?
Yeah.
That is what I call the stair steps. Because they kind of look like stairs, don't they? Now, everything to the left of the stairs is a metal. Everything to the right of the stairs is a nonmetal. Is that a little better? Can you see it? More or less? I think there's an image of it there. So here, everything over here, these are non-metals. Doesn't mean they're gases, just means they're not metal. Over here, all these things are metals, except for hydrogen, which is a gas. So hydrogen is an exception to that rule. Hydrogen is a gas. Yeah?
Can you repeat the
You got to go faster, and if I change slides, please don't call me back because I need to finish this course on time. But right now I'll do it because I'm just in the middle of this. If I were you, I would pay attention to what I'm saying. This is all nonmetals. This is all metals. Now, looking at the stair step, look above and below the stair step. Above and below. Those, above and below the stairs, those are metalloids. Now, the exception to the metalloids is aluminum. Aluminum is a metal. So boron is not as a metalloid. Aluminum is a metal. Silicon is a metalloid. GE is a metalloid. These are metalloids. Aluminum is a metal. So that's your exception to the stair step rule. Above and below the stair steps, except for aluminum, are metalloids. Everything to the right, non-metals. Everything to the left are metals, except for hydrogen, which is a gas. Okay? Now, how do you remember that aluminum is a metal? Everyone in this room has used aluminum to cook with, aluminum foil. If you look at aluminum, you can tell immediately it's a metal, right? It's a metal, for sure it is. It's shiny and it conducts electricity and heat and all that kind of stuff. It's definitely a metal.
Iodine, you talked about they
I can't hear you.
the iodine, they use that to stain specimens.
Yep. Yeah, they do sometimes, for sure. Okay, so metals, nonmetals, metalloids. Write this stuff down. Metals are shiny and ductile, and they're also malleable. So ductile, you can bend them, curve them, make them into shapes, do all kinds of stuff. Nonmetals, they're dull, they're brittle. Metalloids, they're better conductors than metals, but not as good as, better conductors than nonmetals, but not as good as metals. So they're kind of insulating. They're semiconducting. Now, what's an example of a metal? Well, iron, gold. What's another good one? Iron, gold, copper. There's one, good. Nickel. These are things we've all seen before. Those are definitely metals. They're shiny. If you have a strong enough hammer, you can flatten them out. If you have enough heat and enough time, you can bend them and shape them. Non-metals, stuff like carbon. Look at your pencil lead on your pencil. Just take a look at the little black pencil lead on your pencil. That is carbon. That's graphite. That's made of carbon. That is a non-metal. How do we know? Well, it's not shiny, first of all. If you want it to, you could take your pencil lead, you could crumble it pretty simply, right? If you try to conduct electricity through carbon or through graphite, it will work, but not very well. So those are non-metals. Now, metalloids, we don't really experience them much in our society. They, you can buy them as purified elements. We don't have them that way usually. The only one I can think of that you might have seen is silicon, but you've probably seen compounds of silicon. Silicon is a metalloid, and that's used in a lot of computers for semiconductors and computer chips, stuff like that. So that's where most of our metalloid experience comes from. In the lab, for those of you taking lab with me, you'll see examples of all these different kinds of elements, including the metalloids, and you'll see that they look different. They actually have a very different appearance. Metalloids are not quite as shiny, and they're very brittle, actually, compared to metals. But they're not quite as brittle as the nonmetals, which is kind of, sort of neat, right? At least I kind of think so. All right, let's identify each of the following elements as a metal or a nonmetal or a metalloid. Now, the easiest thing to do in a list like this, at least in my opinion, is to find the metals, because there's a whole bunch of them. There's a lot of them. So let's go through that list real quick. First on the list is sodium. Sodium is over here. So is that a metal or a nonmetal or a metalloid? Must be a metal, right? Chlorine. Chlorine is not on the, is way over here. So that must be a nonmetal. Very good. Silicon, there's a tricky one. Silicon's right here. So the stair steps are right there. It's above the stairs. So it's a metalloid. Very good. Iron. You all know iron. You have to look for that one, right? Iron's a metal. And carbon is a nonmetal. Silicon is the metalloid. Carbon is one up from silicon. It's a non-metal. Right? So it's pretty simple, right? There's nothing difficult about this. Am I right? You guys are all comfortable with that? So if I said on an exam, write down all the non-metals, you could do it, right? Boron, silicon, whatever that is. These ones. Some of these names I'm not familiar with. So these are all the non-metals.
Is AT a non-metal as well?
This one? No, it's on the right hand. This would not be a non-metal. That would be a non-metal, not a metalloid. Yes. So you said it was a non-metal, right? Yeah, so it would be a non-metal. But not many people use that one as radioactive. It'll hurt you. Okay, let's go to the next thing. The atom. Now, pay very close attention, because now we're going to talk about the atom. The atom is a very important concept in chemistry. It's something that you really have to understand in order for all of this stuff to kind of make sense that we're going to talk about moving forward. Now, we've talked before about how all matter is made up of atoms. So our life, your life, everyone's life is made up of atoms. Don't write this down. Just listen to me for a second. There's this guy called Dalton back in the day. He had his idea of an atom. Dalton knew, I believe he knew about protons and electrons. And he thought these particles were scattered amongst an atom like raisins in a pudding. Now remember, English pudding is not like American pudding. English pudding is more like a cake. So he thought that the raisins were the particles and they were scattered all through the pudding. So he thought that it was random, more or less random. And he also theorized that atoms could combine to make other things. They could do chemical reactions and make other things. So that was his idea, which was a good idea. Turns out that Dalton was right about the protons, electrons, and the neutrons. Now, let's write these down. A proton is a positively charged particle. Let's write it this way. A positively charged particle, abbreviated with a plus sign. An electron is a negatively charged particle. Is a negatively charged particle. So you have protons that are positive, electrons that are negative. Protons are positive, electrons are negative. And we have these things called neutrons. Neutrons are neutral. They have no charge at all. No charge. So protons, neutrons, and electrons. All of these things make up the atom. Dalton knew that. Dalton figured that out. So now, protons are positive charges. Now when positive charges come together, they repel each other. All right? When negative charges come together, they repel each other. When a positive and a negative charge come together, they attract one another. Okay? Protons and protons repel, so positive and positive push back against each other. Negative and negative push back against each other. They don't want to be close together. They want to be away from each other. But now a plus and a minus attract. So that's where the whole thing, opposites attract, right? That's where that comes from. So now, neutrons are just kind of there for now. So they're just kind of there. So, where exactly are these things in the element? You can write this down if you want, or you can just listen. I would personally just listen. Where are they in the element, or in the atom? Like, where are they located? Along comes this guy, Rutherford. Rutherford did, it was called basically one of the classic experiments in chemistry. What he did was he took a very thin layer of gold, like a very thin foil of gold. He rolled it out wafer thin, like very, very thin. And he put it into a chamber that had photographic paper all around it. So let's just kind of illustrate that real quick. So he took a very thin layer of gold. So just imagine this is a thin layer of gold. Almost transparent, kind of. That's how thin it was. Almost could believe you could see through it. Wasn't that thin, but you get the idea. He wrapped that in some kind of photographic paper. Okay, so he put the gold foil in this circle of photographic paper. And then, by some method, he shot a beam of protons or positively charged particles at it. I'm not sure they were protons. It may have been positively charged atoms. He shot a beam of positive charge at this thing. So these are positive charges coming in here. Positive charges. Positive charges are going towards the gold. All right? So now, you've got very small particles heading towards a foil of gold. What I believe Rutherford probably thought he would see was a whole bunch of these protons bouncing off of here and hitting the walls here, because it should have ricocheted back like a bullet off a wall, right? That's what you'd expect. I mean, gold is solid, right? Things should just bounce off of it. Does that make sense? What he discovered was almost all of the particles passed through it. Like immediately through it, like it wasn't even there. Which must have surprised him. Must have made him go, huh, that's odd. Probably repeated it 3 or 4 times to make sure he was right. He did get some scattering. You get a little bit of scattering, but most of it ended up going straight through, like a bullet through, like through a wall. Like the bullet just went through the drywall and killed someone on the other side, right? So Rutherford was probably very perplexed by this. Probably had to go to the pub and contemplate that with his friends. He was English. So now, what does this mean? What it means is matter must be empty space. Must be mostly made up of empty space. Has to be, because all that charged particle, which is matter, went through a gold foil. Which had to freak you out, right? I mean, if you were the first one to discover that, that would freak you out. I mean, nowadays we go, yes, of course that's how it is. Back in his time, it wasn't how it was. The accepted version was Dalton's version. This was groundbreaking and new. And probably a little scary, because you don't want to buck the trend too much in science or you won't get any funding. Okay, so this must mean that the positive charges must be packed, condensed together. They have to be together. If they were scattered randomly, you would have got random distribution of the ricochets. But because most of it went straight through, all of the plus charges must be pretty much housed together. Does that make sense? It have to be, right? In order for the protons to miss it, they'd have to be compartmentalized, more or less. Make a little sense? Everybody kind of like that? That's kind of what it says. It says more than that, but we'll just leave it there. So matter is mostly empty space, and the protons must be compartmentalized into some area. Okay. And here is what was discovered by this experiment. The protons are in something called a nucleus. There's a nucleus in the center of the atom. That is where the protons and the neutrons are. So in the center of the atom are the protons and the neutrons, and that's called the nucleus. That's where the protons and neutrons are housed. That's where they are. Okay? Protons and neutrons are in the nucleus. So the nucleus is positively charged. In fact, for gold, it's very densely positively charged. There's a lot of positive charge going on right there. And around the nucleus, in some fashion, around the nucleus, is the electrons. The electrons are somehow circling the nucleus. Now, the conventional way of looking at this is wrong. A lot of textbooks, I've seen it in high school textbooks, they will say the electrons are circling the nucleus like planes around an airport. Nothing can be more incorrect than that. That is absolutely not right. We, as a matter of fact, do not really know where the electrons are. It's impossible to tell. We know where they should be. We know where their energy would be the minimum, but we don't know where they are. In fact, the leading scientist in this, Heidelberg's uncertainty principle, he has said, I've read it in his manuscripts, that in order to know where the electron is, we must consider the entire universe. That's how uncertain we can be about where things are when it comes to the electron. Now, that being said, our predictions are probably very accurate. Why? Because stuff works. This chair, for example, doesn't fall apart. So we must be fairly accurate, but we can't say for 100% certainty where electrons are. What we do know is where they should be. We can calculate that using calculus and all kinds of crazy math, figure out where the electrons should be. Does that make sense? So don't think that that whole theory that you've seen where the electrons fly around the nucleus like airplanes, although it looks cool, is completely wrong. Okay. Write that down. Atomic mass unit, please. Atomic mass unit. The top point is probably very confusing. You don't have to write it down if you want. It basically is just telling you where all these other numbers come from. What I do want you to know is that a proton has a mass unit of about 1 AMU. AMU is atomic mass unit. So a proton is about 1. It's a little bit heavier than 1, but it's about 1. A neutron is also about 1. So a proton and a neutron are about the same size. Neutron's a little bit heavier, just a little bit heavier than a proton. But for all intents and purposes, a neutron and a proton have the same mass. And the electron, comparatively, is very small. So look at the number for the electron, 0.000549. So it's way below 1. Excuse me. It's way below 1. So protons, AMU, atomic mass unit of about 1. Neutrons are about 1. Electrons are very small in comparison. But notice, and note down in your notes, the electron does not have 0 mass. It does have mass. So it has mass, it must also take up space. At least that's the theory, right? If it has mass, it must take up space. So the electron also needs room. Okay? Protons, 1 AMU plus charge. Electrons, for all intents and purposes, 0 AMUs, negative charge. Neutron, 1 AMU. Okay? That's just how it is. Can you accept that? You're all good so far? All right, let's get to something cool. Which of the following subatomic particles fits each of the descriptions below? So your choices are proton, neutron, and electron. A is found outside of the nucleus. Electrons, very nice. Has a positive charge. Proton. And has mass but no charge. Neutrons. Right. Very good. It's pretty simple, right? You guys are outstanding. All right, write this down for our subheading. Atomic number and mass number, please. Atomic number and mass number. Atomic number and mass number. One more time. Atomic number and mass number. Now, let's look at the table together, shall we? Right here in blue, written on the top right-hand corner. Now, this table is set up to have that number in the top right-hand corner. It could be in the top left. It could be in the center. I've seen them in the bottoms. You just kind of have to read the table. There's usually a legend for the table somewhere up top that tells you what everything is. But on this table, it's the blue numbers, top right-hand corner. Those are the atomic numbers. Now, the atomic number is the number of protons. Exclamation point. The atomic number is the number of protons. So let's take a look. If we look at carbon, carbon is element C. Carbon has 6 as its atomic number. So carbon has 6 protons. If you have an element that has 7 protons, it's not carbon. If you have an element that has 5 protons, it's not carbon. Carbon always has 6 protons. It always has, it always will. If by some miracle you can take one of the protons away from carbon, you have just changed the element to a different element. Okay? Carbon always has 6. Now, if we look down here at iodine, iodine has 53 protons. Always has, always will. If you go over here to iron, iron has 26 protons. Mercury has 80. How many does gold have? 79. You follow that? That number always means the number of protons. If you change the atomic number, you change the atom. You follow that? So if you change the atomic number, the atom itself also changes. Pretty neat, right? Nothing too earth-shattering there, I hope. Okay. Now, what is also true? What is also true? Well, all the atoms on that table are neutral. They have no charge. So write that down. All atoms are neutral. And when I say all atoms, I mean all the atoms on the periodic table. You can make them have a charge, but after you make them have a charge, they're called something else. They're called ions. We'll get to that in a minute. But right now, all the elements on the periodic table as their elements. So if you isolate the elements are all neutral. So if you have a hunk of iron at home, that hunk of iron has no charge. There's no electricity, there's no positive, there's no negative charges overall. It's completely neutral. So what does that mean then? Who said that? Good. The number of protons in an atom must also equal its electrons. Okay, if you're neutral. If you're an atom, you're neutral. Therefore, your protons must equal your electrons. The protons must equal the electrons in an atom, because atoms are neutral. Okay? Now, ions, when we get to that, those are not neutral, but they're also not atoms or ions. They're different. Okay? So let's do one quick example real quick. Let's say we're talking about the element sodium. Sodium has how many protons? How do we know that? Atomic number. Protons equal 11. So it must have how many electrons? 11. There you go. So now, protons have what charge? Positive, right? So how many positive charges does sodium have? 11. Make sense? Sodium has 11 plus charges. Okay? So that equals an overall plus 11 charge. Now, we also have 11 electrons. What's the charge on an electron? Negative 1, right? So therefore we have how many minus charges? We have 11 total minus charges for a grand total of negative 11, right? If you add that together, you get a grand total of 0. You balanced your checkbook and ended up with 0. Better than negative. Okay? So that's how it works. Number of protons equals number of electrons, therefore it's neutral. Okay? Now, from this information, right now, can you tell the number of neutrons? In fact, I'll just tell you, there's no way at this point to tell the number of neutrons. But I'm going to show you how to do it. Okay? So far, so good, right? So that's how that works. Now, let's get to something fun. This went over that, went over that, went over that. Okay, mass number. Mass number. Write down everything you see there, please. And I will say this, and I'll say it numerous times, because people always forget this part. There it is, bottom point. The mass number, bottom point, does not appear on the periodic table. You can look at that table all day long, and you can never, ever, ever get a mass number. Ever. I don't even think there's a, well, there probably is some for atomic energy guys, but I don't know of any periodic table that has the mass numbers printed on it. For certain, you'll never see one, unless you look it up online. I'll never show you one because I don't think they exist. So, the mass number. The mass number is the number of protons plus the number of neutrons. So the number of protons plus the number of neutrons. That's a mass number. Looking at the periodic table, there's no way to know a mass number. There's just not any way to know it. You have to be either told the mass number, or I'll tell you the number of neutrons. I've got to give you one or the other. I can't expect you to look at that table and go, oh, gold has 15 neutrons, because there's no way to tell from the table. I either have to give you its mass number, or I give you the number of protons. I'll give you one or the other. I have to give you that. Okay, so let's say we have, I don't know, phosphorus. Element P, phosphorus. Let's say we have phosphorus with a mass number of 32. Now, mass numbers are always written there. Whenever you see an element, the mass number will always be written there. It doesn't have to be 32. It can be any whole number. But on phosphorus, I'm picking element number 32. So the mass number is always superscripted on the left of the element. That's where it always is. Go ahead.
I thought you couldn't see it on the periodic table.
I made that up. I just grabbed it from my head.
Oh, okay.
I totally made that up. Actually, I know that phosphorus has a mass number of 32. I know it does. I just kind of know it. It's a radioactive element that's used very commonly. Okay? So I picked it from random. I could have put 58. Wouldn't have mattered really. Okay, so the mass number is always put superscripted on the left. Okay? That's the mass number. You may or you may not see the atomic number written here. You may or you may not see it there. I may write it, I may not. But it's no big deal. The atomic number is on the table. So we run over here to the table and we look at phosphorus. We say, okay, phosphorus has an atomic number of 15. So we run back over here and we stick 15 in there ourselves. 15. That's the mass number, that's the atomic number. Okay. If I gave you this on the exam, phosphorus 3215, that's the mass number, that's the atomic number. Using that formula, you can figure out the number of neutrons, can't you? One equation, one unknown. Pretty simple, right? So the number of neutrons equals the mass number minus the number of protons. I just rearranged that formula to solve for number of neutrons. So number of neutrons is this minus that. Pretty simple, right? That will be on your exam. Promise. It's usually a little table with about 10 points. What? Oh, yeah, sure. Okay. Now, mass number is 32 minus the number of protons, which is 15. Everyone see that? 32 minus 15 is 17. Very good. 17 Not hard, right? It's just subtracting. The key is remembering what the mass number is. I believe it's on your formula sheet, so you don't have to remember it. Knowing what the mass number is, knowing what the number of neutrons are, knowing that you can always go to the periodic table to get the number of protons. So now, let's do an example. I'm going to pull this example completely from my head. So now, let's look at another example of this. What if I say, on an exam, and this is just like me to do this, because it's a very good question that tells me if you know everything about the atom that you need to know. What if I said we have carbon with a mass number of 12? So it's carbon 12. So that's all I tell you. I say, from that information, tell me the number of protons, the number of neutrons, and the number of electrons. You should be able to do it. Right now, you should be able to do it. Take a second, try to figure it out. Hopefully you all can do it. I'm sure all of you can. I just want to make sure. It's not hard, so don't think it's hard. Number of protons, number of neutrons, number of electrons. And the name of the element, which is carbon. But on the exam, I may ask you what the name of the element is. Just look at the table and read the name off the table. It will be there, I promise.
You're not giving the atomic number or anything on the table?
Oh, the table will have atomic number and name and everything else.
Okay.
It'll be a standard table.
Okay.
It'll have everything you need. On the exam, I always answer that question like this, between 1 and a million.
1 in a what?
1 in 1 million. What if it was one question that was really hard or 15 questions that were really easy? Does it really make a difference? But don't forget your Scantron though. You will need a Scantron, 50 questions per side. I do not supply Scantrons, and I do not mark it if you don't have a Scantron, so make sure you have one. I didn't say that. I said you had to have a Scantron. Everyone catch that, right? You need to have a Scantron. I do not supply Scantrons. If you don't write your answers on the Scantron, I won't grade it. So make sure you have a Scantron. Pretty simple, right? Please do that. You can usually buy one from someone the day of the exam, but the price goes way up at that point. I'm not allowed to sell Scantrons. I'm also not allowed to give them away. Everybody get it? Who got it? Who's still cranking it out? One person. Okay, keep going. Give it another minute. Make sure you can get it. Try that one again. The other two are right. Bottom one. Try the electrons again. Because all atoms are neutral, right? So if all atoms are neutral, the positives and the negatives must be equal. Electrons are negative, protons are positive. So they must be the same. Very good. All right, so everybody's pretty much had a chance to work on it. How many protons must carbon have?
6.
How do you know it's 6? It says it where? Right, and what's that called? Atomic number. Number of protons or number of P's is 6. Okay, so now, what is the charge of an atom? They're neutral, so there's no charge. So the number of electrons has to be? Everybody? 6. Number of E's, number of electrons, must be 6. And now the tougher question, but not that tough. How many neutrons?
12 minus 6.
Right, so the number of neutrons, the number of N equals 6. Now for those of you who may not understand how we got that, mass number equals number of protons plus the number of neutrons. The number of neutrons equals the mass number minus the number of protons, which becomes 12 minus 6, which becomes 6 neutrons. Oops. All right? That's where we get the 6 from. Is everyone kind of happy with that? A little bit? Not too shabby, right? All right. So that's the kind of calculations you're going to need to know how to do. So here's another example for you. An atom of lead has a mass number of 207. Calculate the protons, the neutrons, and the electrons of that atom. Lead on the periodic table is right here. So lead's right there. So what's the atomic number? 82. Everyone say it loud. 82. It's 82. So the atomic number is 82. Give yourself a few minutes, try to figure that one out. See, that's how you do it. Good job. Sorry that you're bored. Good job. Do it. You can do it. That'll do it. Did you get it? Oh, which one? Oh, it's 207. Yep. No worries. Number of neutrons. Yep, that's right. Number of electrons. Good. Very good. Did you get it? What is that one? Oh, no. Mass number is the 207 minus 82. See, it says the mass number, 207. Good. Very good. Yep, you'll get there. Be careful with your subtraction, though. Looks good? Yep, looks good. Looks good, looks good. Looks good. Good. How'd you do? Looks, oh, let me see what you got there. So if you're looking at the neutrons, you're correct. The number of protons, if you look at the periodic table, lead is at the very bottom. Number 82. Okay, so 82 is the atomic number. The atomic number is the number of protons. And the number of protons and the number of electrons are always equal in an atom. Good job, though. You got the hard part. How'd you guys do? Did you guys get it? Yeah, good. What's the number of electrons? Excuse me. Yep, looks good. How'd you do? Got it. All right, good. All right, so for the most part, everyone's doing okay. It's not hard, right? It's actually fairly simple, I think most people would say. So make sure you can do that for the exam. It's not hard. It's kind of one of those questions I throw out there just to make sure you get at least 10 points. You'll all do better than that, I'm sure, but it's one of those questions that get you warmed up. You know, it's easy, kind of get it out real quick, and you get your confidence up a little bit. Write that word down, isotope and mass number. Excuse me, I'm sorry.
Are you going to go over it?
Over what?
The problems you just gave us.
Oh, everyone got it right. What's the answer? How many neutrons?
125.
125. Did everyone get 125?
And proton is 82.
There you go. How many electrons you got?
82.
You could have done it. You want to do it? You sure? You did well? Did you get 125? Give yourself a high five. There you go. That was kind of a mid-five, you know. There you go. No, you got it right. So everyone's confident with this? That's why I didn't go over it, because I think everyone's pretty confident with this. You guys are all right? Seriously? So if I, on an exam, no problem. Now, my advice to you guys, and I'm not trying to be mean or anything like that. I'm trying to get you to do what you need to do. You think you have it right now, and maybe you do, but what if you come here next Friday and you don't have it? Then you're going to miss 10 easy points. Make sure you do the homework. Make sure you can crank them out. Because if you can do it on the homework, you can do it on the exam. And it's 10 easy points. Okay? So don't let 10 easy points go by just because you didn't practice. Okay? So please go home and practice it, even though it's easy. You still need to make sure your confidence is really high. All right. Isotopes and mass number. An isotope, write all of that down, please. Isotopes are interesting. Let's just say it like that. They're interesting. Isotopes have the same mass number, so they're the same element. Sorry, they have the same atomic number. They're the same atomic number, so they're the same element, but they have different mass numbers. Same atomic number, different mass numbers. Okay? So an atom has the same atomic number. So all atoms of carbon have the atomic number 6. But not all isotopes of carbon have a mass number of 12, for example. Okay? So the same atomic number, same number of protons, different mass number. So if you have the same number of protons, different mass number, what's changing? The number of neutrons. Okay? So that leads me to this. If I come into class one day and I say, what makes an atom an atom? The number of protons. Okay? So what makes a nitrogen atom a nitrogen atom? The fact that it has 7 protons. Okay? What makes a carbon atom a carbon atom? It has 6 protons. That's what makes it the atom that it is. Now if I were to say, what makes an isotope? The number of neutrons. Okay? Neutrons change the isotope. All right? Atoms are defined by the number of protons. Isotopes are defined by the number of neutrons. Okay, or the difference in neutrons, or difference in mass number. Now, let's take a look at an example. Carbon is a great example. Carbon 12, carbon 13, and carbon 14. All of them are carbon. They're all carbon. Okay? They all have the same number of protons. How many protons does carbon have? How do you know that? Atomic number that you get off the periodic table, which you will get on the exam. It'll be stapled to the back. Real quick, let's leave you to this point. On an exam, if you want to tear the exam apart, have papers all over your desk, feel free. If you have the room. So don't, you don't have to ask me if you can tear the periodic table off the back. Go ahead and tear it off. I don't care. But just make sure you know that it's on the back of the exam. It'll be the last page. Okay. Carbon 12, carbon 13, and carbon 14. So this is the mass number. Mass number. Mass number. Mass number. The mass number is changing. It's going up by 1. I believe those are the 3 most predominant isotopes of carbon on the Earth right now. They're the most predominant. Carbon 12, I think, is I'm not sure if carbon 12 is the big one or not. but there's a lot of it. Carbon 13, carbon 14. So now, in this isotope of carbon, the number of protons equals 6. Is that correct? In this one, the number of protons are 6, and in that one, the number of protons are 6. Does that make sense? They're all carbon, right? So they all must have 6 protons. Are we good with that? Yes. They all must have 6. So therefore, if they're atoms, they must have how many electrons? 6. So they're neutral. If they're atoms, they must be neutral, so they must have the same number of electrons and protons. Now, the mass number equals the number of protons plus the number of neutrons. So the number of neutrons then, rearrange the formula, equals, there you go, mass number, number minus the number of protons. So for the first one, it's 12 minus 6 is number 6, right? So for this one, 12 minus 6, number of neutrons, equals 6. For the second one, it's 13 minus 6, right? Different mass number, 13. Subtract 6 from that is 7. So this one has 7 neutrons. And the last one, 14. The 14, I get it from right here. Mass number minus 6 equals 8. So that one has 8 neutrons. See the difference? That's the only difference. Just those extra neutrons. Okay? Is that pretty straightforward? Okay, now, what difference does that make? A big difference, actually. I believe it's carbon 13. I could be wrong, but I believe it's carbon 13 that's radioactive. It actually will decay. Carbon 12, I think, is not radioactive. And carbon 14, I don't think is either. But I think carbon 13 is radioactive. So it makes some difference. It does make for some elements, it makes a huge difference. So that's what isotopes are. Let's get to a learning check. There you go. Oh, we just did that one. Crap. Let me give you another example up here. That's the learning check. We just did it right here. I didn't mean to do that. Let me give you a different example that you can work on. What if I gave you, let me think of an element real quick. Oh, nitrogen. Now let's do something bigger. That's too small. How about bromine? What if you had bromine 81, bromine 82, and bromine 84? So I skipped 83, just for fun. So those are 3 isotopes of bromine. Go ahead and figure out the number of protons, number of neutrons, and number of electrons. The carbon learning check, I just did it by mistake, sorry. But try that one out for size. It's the same procedure as carbon, just the numbers are a little bit bigger. No big deal for you guys. Bromine's right here in the old periodic table. Its atomic number is 35. So give that one a try. Give that one the old college try, as they say. Excuse me.
Are they always have more neutrons, or can they have less?
No, they don't always have more. They can certainly have less.
More.
Less than the number of protons, you mean?
Nevertheless, it's like, for example, they cannot have less...
Less neutrons than protons?
No, less neutrons than the regular ones. For
I
example,
don't understand.
Yes. The atoms,
Mhm.
if they are atoms, they usually have the same number of protons and neutrons, usually.
If they're atoms, they have the same number of protons and electrons. The neutrons always change.
Well, yeah.
Okay.
I know that's an average. Okay.
Okay, you sure?
Yeah.
Are you sure? All right. It's like you're bored now. Good for you. Looks good. comfortable with this? Good. You look good. Looks comfortable. How you doing? Oh, out of the park. Good for you. Yep, looks good. It's really, really encouraging. Everyone seems to be really getting this down. How you doing?
Good.
You sure? Where's your answers at?
I'm still there.
Oh, you're still cranking it out? How you doing? All right, so how many electrons do you have in that first one?
Yeah, I did.
Okay, it's really, really simple at this point. In an atom, the number of electrons equals the number of protons, because all atoms are neutral.
Right, but would it be like, I'm just trying to, would it be like a negative or would it?
Oh, you could put negative if you wanted to, or you could just put 35.
Okay, that's where I was confused.
Yep, you could either put negative or 35, negative 35 or 35. I'd take both. Good? How you guys doing? That looks pretty good. Yep.
Just a little.
You're confused with what?
No, because I was like, the thing is, I was asking her, how do you get 35? And she was explaining to me,
Oh.
it's going to be the number that's
Yeah,
on the top.
the blue number on this table. It may not be on the top right-hand corner on the table on your exam, but it'll be obvious which one it is.
I just have to go home and do my homework.
Yeah, if you're doing okay right now, I can see. So when you just do your homework, you just get better at it. That's all. You guys doing all right? How you guys do? Let's see. You hold up for me. Oh, well, did you get the numbers right?
I had the numbers right, but I'm
And then you're good.
Am I doing it the same way we did the first one here?
Hold on a sec. Yeah, you look good.
Okay, but I'm trying to
Yep.
find that one.
So those are the number of what? What are these numbers here?
yeah.
Number of neutrons. Very good. So how many protons do we have?
35.
How many electrons?
30, negative.
You got it. Good job. Did you get it? Well, okay. So let's do this one together. Bromine 81. Let's do that one. So write down Br 81. All right. So the 81 is the mass number. So that's how many protons plus the number of neutrons. Okay. So now, if you look at the periodic table, Br is number 35. It's on the fourth row down beside Kr.
Yeah.
So it's got a mass number, atomic number of 35. The atomic number is the number of protons. So that's the number of protons. So write down number of P's or number of protons to remind yourself. Equals. There you go, protons. All right, so it has 35 protons and 35 electrons. Because atoms are always neutral, so they have the same number of protons as electrons. Now the difference between these three is they have a different mass number, 81, 82, 84. So you subtract the number of protons from the mass number. So 81 subtract 35, that's the number of neutrons. So that's how you can figure out all three just by knowing the mass number and the element, of course. Looks good? Looks good? Yep, good? How'd you guys do over here? You got it. You're good now. Good? How'd you do? I didn't ask you. You guys. Looks good? Looks good? You guys are doing great.
You asked me.
I don't have to ask you. I already know. You're just smoking awesome. Yeah, see? I knew it. Sometimes you just know. You know what I mean? How'd you guys do? Did you guys get it?
Yes.
All right. So is everyone confident with this? Yeah? All right. Let's go through this. Number of protons. Number of electrons. Number of neutrons. Now, bromine's atomic number is? 35. So it has 35 protons, yes? Yes. Everyone? Yes. All right. So what makes an atom an atom?
The proton.
The number of protons. So if I have bromine, has 35 protons. What if I gave bromine one more to make it 36? What would happen?
It's not bromine.
It would not be bromine. It would be something else, right? It'd be a different atom. Outstanding. How many electrons? 35. All atoms are neutral. Now, we can give them charges. We'll learn about that later. Those aren't atoms. Those are ions. And the number of neutrons. Well, that's a little tougher.
81 minus 35.
Mass number, yep, I think that's correct. 80 mass number equals number of protons plus the number of neutrons. So the number of neutrons equals the mass number minus the number of protons. So for these ones, it will be 81 minus 35, 82 minus 35, and 84 minus 35, which gives us, what is it, 41, 46, 47, and 49?
Yes.
Very good. Everybody confident with this? Yeah. All right, very good. Very, very good. Very good, very good, very good. All righty then. Moving right along. Atomic mass. Now, just go ahead and write those 2 points down. I'm not going to ask you to know how to calculate an atomic mass, but I do kind of want you to know what it is. The atomic mass is not the mass number. The mass number and the atomic mass are different. The mass number is the number of protons plus neutrons. The atomic mass is the quote-unquote weighted average of all the naturally occurring isotopes. Okay? Now we've drawn out these isotopes, carbon-12, carbon-13, carbon-14, for example, but they don't all exist on the Earth in the same abundance. I believe carbon-12 is like 95% of all carbon. So if you have 100 carbon atoms, 95 of them, I think it's 95, would be 12 would be the mass number. And then the other 5% would be between 13 and 14. So there's a lot more carbon-12 on the Earth than there is carbon-13 and 14. Does that make sense? Because 95% of all the carbon that we have is carbon-12. So when you do what's called a weighted average, is you take into account the fact that there's a lot more carbon than there is carbon-12 than there is carbon-13 and 14. That's all that means. So the weighted average just simply means that you weight your average towards the most abundant isotope. And there's a whole series of math you do to figure that out. It's not that challenging. It's just not all that important. Okay? So, and the mass number is this red number right here. So all the atoms have it. This red number down here on the bottom. So for potassium, it's 39.0983. That is its atomic mass. This is the atomic mass. It is not the mass number. Okay? It's the atomic mass. So let me draw that up here.
The atomic mass will make the atom an atom, right?
The atomic mass? No, the atomic mass is the weighted average of all the isotopes. So you take all the isotopes and you kind of make an average of them. So you get the average atomic mass. The atomic number is what makes an atom. So let's take sulfur, for example. On that periodic table over there, sulfur says 16 like that. And what's the mass? 32.066. So on that table, this is the atomic number. That is the atomic mass. And let's write this in a different color just to drive it home. This is not the mass number. Okay? Atomic mass. This is not the mass number. The mass number is never printed there. If you want to think of a way to remember that, the mass number is a whole number. What does that mean? The mass number will never be a decimal point. You can never get a mass number of 5.2. It's either 5, or it's 6, or it's 4. It's never 5.2. Now the atomic mass is almost always not a whole number. It's almost always got decimal points. There's a few exceptions that you can see on there, but almost always it has decimal points. So the atomic mass is this number right here, has decimal points. The mass number is always a whole number, so it is not the atomic mass. They're different. Now, I'm going to say it one more time. The atomic mass is not the mass number. The mass number is always a whole number. Always. So there's never a decimal point. Somebody on the exam is going to write down a mass number and just read the atomic mass off the periodic table. There's always one person who does it. Don't let it be you. Okay? The atomic mass is almost always not a whole number. The mass number is always a whole number. Okay? The mass number is not printed on the periodic table. The atomic mass is. Okay? So please don't be the one to get that wrong. So, now that you've had a little break, time to absorb all that information, let's have a quick little refresher. What makes an atom an atom?
And the electrons.
The protons. The electrons don't. But you're being a little overzealous. I like that. I like that.
They always have the same protons and electrons.
If it's neutral. If it's neutral. We're going to learn soon when it's not neutral. It's going to be negative or positive. But good. Overzealous is always better than underzealous. Now, what makes an isotope an isotope? Number of neutrons. So the number of neutrons will change depending on the mass number. What's the mass number? There you go. Number of neutrons plus protons. Very nice. What's the atomic mass? The what is it? Close, yes. It's the mass of the element. Right. It's the weighted average of all the naturally occurring isotopes. The weighted average means that you'd cheat your average towards the most abundant because there's just more of it. But you're more or less correct. You got the idea. What do you find on the periodic table?
At the bottom.
And this table is at the bottom and it's written in red. Where do you find mass numbers on the periodic table? You don't. Ah, very good. Can't trick this crowd. Very good. Now, electron.
Question on the test.
Huh?
Ask it.
I probably will. I better. You better get it right. Because now you've asked for it. See, students ask me for questions all the time, so I put them on the exams, and they're like, why'd you put that on there? So, yeah, I probably will ask you that. So, but maybe not in those words, but the same spirit. See what I'm saying? All right, electron energy levels. Please write that down as the topic heading. Now, electrons have energy levels. You can write down the next slide if you want, or I would just look at it if I were you and follow along. I'm going to draw some stuff on the board that I think will help you a little bit better. The atoms have energy levels, or the electrons. Now, the electrons, remember, they're repelling each other, so they can't stand each other. It's like being in the same room with your arch nemesis, but you got to be there. Why? Because the protons are there. Your whole goal as an electron is to get close to the protons. By doing that, though, you're forced to come into close proximity with those nasty little electrons. And they're repelling you and you are repelling them. So all of the electrons can't be at the same place at the same time. They're going to repel each other. So let's look at it this way. If you live down here in Florida, which we all do, we all know that the best real estate around is beachfront, right? That's the most expensive and the most desired. Personally, I would rather not live there. I like being away from the ocean because that's where the hurricanes come from. Now, so the ocean is like the desired spot. So let's think of the nucleus as the ocean. Let's just think of it as the ocean. It's not the ocean, it's a nucleus. It's full of protons. So there's tons of positive charge right there. And the positive charge, because you're an electron, is an attracting force. So you want to be like, oh, the protons are so beautiful this time of year. Okay? So now, we're going to build a street. We're going to build a street. So that's a street. That line is just a street that surrounds the ocean. Now, there's limited space on that street. Make sense? There's limited space by the ocean. There's limited space by on the street of the atom. This is the first shell. So write down first shell, or the one shell. That's the first street in our little neighborhood. So now we all want to be close to the positive charges because we're negative. We want to just get close to those positives. So now, we all want to try to live on the first street, or the shell number 1. That's a shell. Now this shell, don't confuse it. That is not a flight path. That is not the flight path the atom takes, which is where that weird misnomer that people see of the electrons flying around the neutrons. This is where it comes from. But this is not a flight path. What that is, think of it this way. Take a pea, like a little pea that you find in the cans and frozen and fresh, those little vegetables, and then get a beach ball. Blow the beach ball up and put the pea in the center of the beach ball. That shell is the beach ball. Okay? The outside of the beach ball is the outer part of that shell. The electron can be anywhere from the outside of the beach ball to the nucleus. It could be anywhere in there. So all this is a prediction of where the electrons should be. See what I'm saying? So it's not a street, really. I call it a street because it makes it easier to remember. But it's a prediction of where the electrons should be. Okay? All right. Now, because there's limited space on that street, only 2 electrons can live here. Only 2 electrons can live on that street. Because there's limited space, properties at a premium, not everyone can afford it. Only 2 electrons can live there. So the first shell of any atom, only 2 electrons can live there. Only 2. So now you're the mayor of our little town, and you want more tax revenue. So what do? You build more streets, right? So now, draw another circle. That's another energy level. So now instead of being right beside the ocean with a view, now you're 1 street away. So instead of being on A1A, now you're back at, I don't know what, Federal, right? Or Dixie. So you're back off the ocean. Not so bad, you're pretty close, but you're not right on the ocean, so you're not as happy as you could be. But now, you've gotten further away, so you're a bigger street, right? Because you can even see the circumference of this circle is bigger than that one, right? So it's a bigger street. Larger streets can hold more people, right? The larger shells can hold more electrons. This is the second shell, or the 2 shell. And it can hold only 8 electrons. The second shell can hold only 8. Now, can it hold less than 8? Absolutely. Could it hold 0? Yep, no one lives there. Could the first shell have less than 2? Absolutely. It can have 1, it can have 0. No problem. No more. They can have less, but no more. Very good. So the first shell could have 2, 1, or 0, but not 3. The second shell can have 8 all the way down to 0, but no more than 8. So we build a third shell. Another street. It's bigger. The third shell, or the 3 shell. That will hold only 8 as well. But when times are good and there's lots of people, we'll build apartment buildings, and we could hold maximum 18. Usually, most of the time, it only holds 8. There are examples, though, where people will move into apartment buildings and we'll put more people on that street. But for this class, we stop at 8. Okay, so we'll just stop at 8. But just know it could hold 18 if we had to have 18. It could. But for this, our class, we only say 8. Because it just makes life a little bit easier for all of us. But know that it could hold maximum 18 if we had to force it. Okay? Everybody okay with that? Okay. So now, the ocean, the nucleus, plus charge, all the electrons want to be around it. The further out you go from the nucleus, the more electrons you can hold. The closer you get, the fewer electrons you can hold. This, the first shell, is the low energy shell because it's the closest to the plus charge. The closer you are to the plus charge, the lower your energy is. Okay? Make sense? Because you know yourself, when you go to the beach, what do? You relax. Your stresses goes away. You drink a little water or something adult, and you relax. If you go for a swim in the ocean, right? As you move further away, you get out into traffic, and those crazy Canadians, I'm a Canadian, I can say that, the crazy Canadians cut you off because they don't know where they're going. It happens. You get stressed out. So the further away from the ocean you get, the more stress you obtain. All right, now, how many electrons can the first shell hold? 2. This is the first period of the periodic table. How many atoms in the first period? 2. This is the second period of the periodic table. How many atoms? 1, 2, 3, 4, 5, 6, 7, 8. Curious, right? The third shell. 1, 2, 3, 4, 5, 6, 7, 8. That's interesting. And I said 18, right? It could hold maximum of 18. Don't write this down because this is going to confuse you. The other 10 are right here. Okay? That's why we stop at 8 for the third shell, because the other 10 for the third shell are located in the fourth shell, which is completely weird for you guys, so don't even think about it. But that's where they are. They're right here. Okay? So, but for this class, I just tell you where they are so you'll kind of know, but don't worry about that. Just worry about the 8. Okay? Follow me? Know the third shell can get 18, but don't worry about it. Just worry about the 8. Okay? So now, I think I've convinced you that the periods and the shells are the same. They line up. The first period is the first shell. Okay? Does that make sense? The second period is the first shell plus the second shell. Make sense? All right? So everyone's kind of okay with that? All right, very good. Let's get to a question. I won't do all this. Come on. There we go. Write this question down and circle the words electron arrangement, please. Write the electron arrangement for the following elements. I'm going to teach you by way of example what all those slides I skipped over are saying, because those slides I think are a little confusing. I couldn't say it any better. I think just doing examples is the way to learn this stuff. But circle the words electron arrangement. We're going to draw the electronic arrangement. Remember when I told you at the beginning of class, I can look at that table and I can tell you the mass, I can tell you the atomic mass, the atomic number, what the element's called, and where the electrons are? Yes. Right now, I'm going to teach you how to do it. And it's really simple. You won't believe how simple this stuff is. Now, electron arrangement. What that's asking you is, where do the electrons live in your little city, in your little atom city? Where do they live? Remember, electrons always want to be close to the ocean or the nucleus. They always want to be close. So when you're putting electrons into their shells or their little roads or their energy levels or whatever, you always fill up the low energy first, right? Does that make sense? You always want to fill the low energy streets first because, that's where people want to be, right? That's where electrons want to be too. They want to be low energy. So now we look at carbon. And we're going to write the electron arrangement of carbon. The first question, if you're going to answer this question, the first question you have to answer is, how many electrons live in carbon? 6. Its atomic number is 6. It has 6 protons. It must therefore have 6 electrons. Where do those electrons live? Well, we're going to put 2 in the first shell. Right? Because that's the low energy street. So 2 of them are going to go in the first shell. How do we write that? You just write the number 2. Just put a 2. 2 stands for 2 electrons. Sorry. Now, we have a grand total of 6 electrons. So let's write that down to remind ourselves. We have 6 electrons that want to come live in carbon. We've already placed 2 of them on the first street. So there's 4 left to go, right? Let's count on the periodic table. Let's just count. So the first 2 went here on the first shell. So the first 2 went here. Hydrogen, helium. 1, 2, 3, 4. So there's 4 on the second shell. Does that make sense? Don't count the little squares as atoms. Just count them as little holes you can put electrons in. So there's 4 on the second shell. Make sense? There's 2 on the first shell, 4 on the second shell. Okay? So in your little atomic town, 2 electrons live on the first shell and 4 are on the second one in carbon. Is that okay? All right, let's do silicon. Si. How many protons does silicon have?
14.
Everybody see that? 14. So how many electrons is that? There you go. So now, on the first shell, or the first street, how many electrons? 2. How many on the next street? 8. And how many on the last one? 4. This is the first, or 1 shell. That is the 2 shell. And that is the 3 shell, the 3rd street. Let's go over to the periodic table. You can count it. If you don't remember how to do it, just count it from the periodic table. So here's silicon. Here's where we want to go. Okay? Now, all these squares, imagine they're not elements. They're just empty spaces. So if you want to get to here. You want to get to here. So how would you do it? Well, you start here. First shell. 1, 2. Go back over here. 2 in the first shell. 1, 2, 3, 4, 5, 6, 7, 8. 8 in the second shell. You go all the way over here. 1, 2, 3, 4 in the third shell. Just imagine that all those spots are not elements, they're just empty blanks. And just count. 1, 2. Just put electrons in them. Does that make sense? Is that pretty simple? Excellent. All right, let's do another one. Oxygen. You breathe it every day. Tastes good on ice cream. It doesn't really. Oxygen. How many protons does oxygen have? 8. Oxygen is element O. It has 8 protons and 8 electrons. So now, how many electrons are on the first street, or the first shell? 2. And how many are on the second one? 2 and 6. Very good. It's pretty simple, right? And the last one, nitrogen. Excuse me. Nitrogen has how many protons? 7. So it has how many electrons? 7. Nitrogen, 7 electrons. So that's going to be 2 and 5. Pretty straightforward, right? There's nothing hard about that. That's where the electrons want to go. Okay, they want to fall into those categories because that's the low energy state. Okay? If you start trying to put more electrons into the first shell, they will repel each other to the point where one of them will be kicked out. They'll just push the other neighbor out. Okay? Let's do one more that's not on there. Let's do argon. Argon. Argon is in group 18. It's right here. So it's in the last group of the periodic table. These are called the noble gases because they don't what? React. They don't react. They don't do much. So argon is a noble gas. It's an unreactive gas. So let's do the electron configuration of argon. Someone said it had 18 electrons. Very good. So let's fill the streets. So how does it work? It has 2, 8, and 8. That's argon. 2, 8, and 8. Let's do the one above it, neon. Neon has how many electrons? There you go. So it's going to be 2 and 8. With a different color marker, circle the last number. Or square it or something. Put a square on the last numbers of those configurations. So now we have the number 8. We have 2 noble gases, neon and argon, with the number 8 as their final number in the electronic configuration. That's a big deal. I know it seems like a small deal. That's a big deal. The fact that argon streets are filled and the number of protons equals the number of neutrons means that argon is very stable. It doesn't want to gain any more electrons. It certainly doesn't want to lose any electrons. But it doesn't, it's just happy. It's content. Some would say it's perfect. Neon has 10 electrons and 10 protons, so that's neutral. And it's got a filled street. All of its streets are filled. 2 and 8. It's done. It's finished. That's stable. Okay? Having 8 electrons in your outermost shell, your outermost street, is a stabilizing effect. Okay? So write that down. That's a stabilizing effect, or that's good, or it's really awesome, or whatever.
Is that in any shell? I mean, as far as...
For what we're going to discuss, yeah, it'll be any shell. Okay, is everyone kind of happy with that? Okay, not hard, right? But you have to know it. All right, trends. Trends in periodic properties. Please write that down. Now, this is like a, well, I call this foreshadowing. We're going to go back to this later on, but I wanted to address it right now that 8, the 8 is like a magical number in chemistry. We're going to get to it in the next chapter. Probably we'll get to it today. Okay, trends. Write this down for me, especially the word valence electron. Valence electrons are the number of electrons in the outermost energy level. Okay. Valence electrons are the number of electrons in the outermost energy level. Simply said, if you look at oxygen, 2 and 6, the last energy level or the last street in your town to be putting people into it is the second shell, right? Or the 2 shell. Yeah. That's referred to as the valence shell because it's the one that's filling up. The second shell. In oxygen and nitrogen, it's the second shell. It could be the third one. We'll do an example. It's the shell on the very outskirts of your city that's getting filled up. So the ones underneath of it are not the valence. They're the ones that are already filled. I'll show you a few examples and it'll be very clear. So those are your valence electrons. Okay? So now, this 6, that's the second shell, right? Or the 2 shell? And that's not filled yet, is it? It only has 6 versus 8, right? So it could take more, right? That's your valence shell. It's the outermost energy level that's being filled with electrons. On nitrogen, that is your valence shell. Those are valence shells. They're being filled with electrons. They're not filled yet, they're being filled. Okay, let's do an example of a period 3 element. Let's do chlorine. Chlorine has 17 electrons, yeah? So that's going to be 2, right? And 8 and 7. So the valence shell of chlorine is the 3rd shell, or the 3 shell. Okay? It's the outermost street or energy level that's being filled with electrons. Okay? So I know I'm making a big deal of it. It's actually a very big deal. You have to look at the valence electrons. Okay? Now on argon and neon, that is the valence shell of argon. That is the valence shell of neon. How many electrons are in the valence shell of argon and neon? 8. Having a filled valence shell is a big deal. Having a filled valence shell is a big deal. Okay? Everyone agree with me? Yeah. Okay? So now, if we do an example, let's do magnesium together. Let's do magnesium. And I want to know the valence shell. So to do that, I would take magnesium, Mg, 12 electrons, right? So that will be 2, 8, 2. How many electrons are in the valence shell? 2. Which shell is it? The 3rd, right? So the 3rd shell is filling with electrons. So the valence shell has 2 electrons. The electrons that are in the valence shell are called the valence electrons. Pretty simple, right? The valence shell is the outermost shell being filled up. The electrons that are in that shell are your valence electrons. Okay? Now, I know I'm harping on this. This is a big deal. The valence shell, the outermost shell filling with electrons. The valence electrons are the electrons that are in that shell. Okay? So for magnesium, this is the valence shell. And the valence electrons. All right, so the valence shell and the valence electrons. So the valence shell is 3, the valence electrons, there's 2 of them.
Like if like for example
Neon.
8 in its outer shell, so
Yep.
it has 8 valence.
Has 8 valence electrons. And it's happy. Okay? So we good with that, right?
Yes.
A little bit? Okay. All right, let's do a couple more real quick because I want to point out one thing that's really fun. Because it's always a good thing to know the valence electrons. So let's do carbon, which is 6, so that's 2 and 4. Nitrogen, which is, not nitrogen, how about phosphorus, which is what? 2, 8, and what? 2, 8, and 5? Yeah. 2, 8, and 5. Okay, now, I can look at the periodic table right now, and I can say calcium has 2 valence electrons, bromine has 7, selenium beside it has 6, nitrogen has 5, boron has 3, aluminum has 3, chlorine has 7. How can I do that so fast? No. Well, that too. But here's how you do it. It's not really that hard. Look at this. 4 and 5, right? This carbon is in group 14. Take away that 1, all group 14 elements have 4 valence electrons. Take away the 1, it's 4. All group 14 electrons have 4 valence electrons.
So that only works for double numbers?
It only works for group 1, 2, 13 through 18. Okay? It works for anything that's not in the transition zone.
Okay, so
So now, if I say fluorine, how many valence electrons does fluorine have? Well, what group is it in? 17, right? Take off the 1, 7. Fluorine has 7 valence electrons. Phosphorus. Phosphorus is in group 15. Take off the 1, it has 5 valence electrons.
so that works for what?
What? Yep, number 1. Lithium has 1 valence electron. Potassium has 1 valence electron. Calcium, beside potassium, element 20, is in group 2, 2 valence electrons. Down group 3 through group 12, don't try this at home because you'll get it wrong. Group 3 through 12 don't follow that trend. They do something completely different we don't discuss in this class.
So that PB, you're going to have fluorine in the electrons?
PB, where's PB? Oh yeah, there should be 4, yep. Now PB is a lead, so PB is lead, which is a metal. They do funny things, but yes, it has 4 valence electrons. Very good. Iodine, group 17 has 7. Krypton, group 18 has 8. Now, the exception to what I'm telling you right now is in group 18, helium. Helium does not have 2 valence electrons, have 8, it only has 2. So, forgive me, it doesn't always work. But it works 99% of the time. It just falls apart for the transition metals and for helium. Helium only has 2. Okay, so we good? All right, one more time. Boron, group 13. 3 valence electrons. I don't know. Selenium, Sc, number 34. Has 6 valence electrons. It's in group 16, must have 6. Right? See how easy that is? No? It's not easy? All right. Electron symbols. Okay, this is important. Let's take magnesium, let's look at carbon, and let's look at phosphorus, and let's look at argon, or neon. So that's 2 and 8. Now, the most important electrons in an atom are the valence electrons. The other electrons have to be there in order to provide stability and all that, but chemically they don't do much. They just kind of hang out. The valence electrons do all the heavy lifting. They do all the work. So it's important to know how many valence electrons we have, and let's face reality, it gets a little tiresome writing this down for every atom. It just gets a little tiresome. It's easier to write down what's called the electron dot symbol. So, for magnesium, we look at the valence electrons, or the valence shell. And we write down the symbol for magnesium is just simply Mg. Okay? And then we say, okay, Mg has 2 valence electrons. So all you got to do, and I'm not kidding, it's this easy, is draw 2 dots. Like that. Yep, I would put them like here and there, or here and there, or here and there. Don't double them yet. I'll show you when you double them. Okay? So don't put them side by side. Just put them anywhere on the atom. Carbon. Carbon has how many valence electrons? 4, right? So that would be carbon, C. Now when I draw electrons, because electrons repel each other, right? They hate each other. So I would do it this way. I didn't do it for magnesium because it kind of looks funny. But for this one, just draw there, north, south, east, west. Just fill it in like that because all the electrons are as far apart as possible. They all have to be there, but they certainly don't want to see each other. You know what I mean? It's like living in the same apartment with your ex. Don't want to see them. They go to work at 7, you go to work at 6:45. And people are laughing because they all been there, right? All been there. All right, phosphorus has how many valence electrons? 5. So phosphorus, now, watch this, and watch very closely. 1, or north, south, east, west. So we filled in all 4 corners of the element. Now we have to start doubling them, which means this. One of these single electrons has to hang out with another. They just draw them like that. They have to hang out with another. These are called single electrons. So they're single and ready to mingle. And they will. Well, I'll show you later how they'll mingle. These ones are called lone pairs. That's a lone pair. Now, I don't know why the word lone is put with pair, but they're called lone pairs. I guess because when you hook up with somebody, you're all of a sudden lonely. Don't know. But whatever it takes to remember it, that's what you should do. So they're called lone pairs, and they will react from time to time. But usually it's the single electrons that do all the work. Okay. So now, oh, sorry, one more. Neon. Neon has how many electrons? 8. Oh, I'm sorry, 8 valence. 10 total, 8 valence. Very good. Very good for you. Neon has 8 valence. So north, south, east, west. Uh-oh. Now we got to start doubling. North, south, east, west. Neon has 8 valence electrons. Therefore, it has 4 lone pairs. Okay? Yeah, because I personally think it looks prettier. And that's how most people draw it, because it aesthetically looks better. And quite honestly, back before computers, when they had to actually typeset this stuff, these are colons. They just use colons for electrons. So it was cheap and easy to do. Quite literally, that's probably where it came from, why there's up and down, not side by side. Also being side by side takes up more space, which nowadays doesn't matter because paper and typing are so cheap. But back when they had the typeset and paper was very expensive, the less paper you took up, the cheaper it was to print. So think of it that way. Okay, so those are the valence electrons drawn in dot format. I think everyone will agree it's easier to look at that than it is to look at that, 2 and 4. Because the 2 and 4 kind of doesn't mean much. I mean, it's just 2 numbers, right? This means carbon with 4 valence electrons. It has a lot more meaning. It's a lot more interesting, a lot more fun. Probably, yeah. It's important, so yeah. All right, so go ahead and try it yourself. Write the electron dot symbol for each of the following: chlorine, carbon, and nitrogen. Write the electron dot format, please. Chlorine, carbon, and nitrogen. While you're doing that, just a quick reminder, there's an exam next week, right? You got to bring your own Scantron, 50 questions per side. When you get here, I'm going to arrange your seating, so don't get upset when I move you guys around. It's not personal. I'm not picking on anybody individually. I always move people around on exam days. Try to put as much space between students as I can, so that minimizes the risk of people looking at everyone else's papers. Not that you would do it, but people do it. So don't take it personally if it happens to you. It's not that I'm trying to pick on you or anyone else. I'm just doing what I always do. For every class, I do it for every class. And don't forget, you have to put your books and book bags against the wall. So be prepared for that. Everything goes against the wall, except for your pencil, pen, eraser, calculator, and your Scantron. Yeah, after the exam, we'll move on with new material.
Oh, okay. Because how many hours? What time?
For an hour and 20 minutes. So do this question now, please. Interesting. Everybody got it? Pretty easy, right? Chlorine's the only one up there that we haven't already looked at. So what's chlorine? How do you draw it? 7 valence electrons. So how many lone pairs do you have?
3.
How many? Very nice. How many single electrons? 1. It's that easy, right? For nitrogen, how many single electrons do you have?
4.
Nitrogen? Nitrogen should
We have
1 lone pair and 3 single electrons, right? So nitrogen has 1 lone pair, 3 single electrons. And carbon has 4 single electrons. All right, so nitrogen, because people seem confused by it, nitrogen has 5 valence electrons. So it's going to be north, south, east, west, and then the 5th one will pair. You can pair the top or the sides or the bottom. I don't care which one you pair. They're all the same. Okay? So that's nitrogen.
You don't have to go north, south.
I do, but if you want to go east, west, south, north, it's up to you. I always put my lone pair on the top because I think it looks nicer. If you think it looks nicer on the bottom, that's cool too. It's all the same. All right, very cool, right? It's pretty simple for you guys, right? You guys are pretty much on the ball here. So I'm really, really happy to see. Okay, atomic size. Atomic size is determined by what's called the atomic radius. That is the distance from the nucleus to the outermost electrons, or to the valence electrons, or to the valence shell, if you will. That's your atomic radius. Alrighty, so atomic radius. Distance from the nucleus to the valence electrons. It increases going down the table and decreases going across the period. Okay, so we're looking at this distance here. So the nucleus is here. And here is our valence electrons. We're looking at this distance right here. We're looking at that distance. So now, as you go down a group, the distance, this distance gets larger as you go down. That should, I hope, make sense. Because as you're going down a group, you're adding more streets to your town. So here there's only 1 street in your town. Down here there's 5 streets. So you've grown 5 times as large. Okay, you have more streets. So they're building further away from the nucleus. Okay? So the valence electrons are getting further and further away as you build up. Okay? Does that make sense? Yes. Everybody? As you're going, yeah, as you move further down the periodic table, so down a group, you're adding more streets or more shells, right? Because remember, the first period is the first shell, the 6th period is the 6th shell. So there's now, instead of having 1 street, you've got 6. So you're building more streets, so your town is getting larger. So your atomic radius should get bigger. Does that make sense? Yeah, the atomic size. increases because the atomic radius increases. Okay? Now, the weird one goes left to right. From left to right, they get smaller. So as you go from left to right, the atomic size decreases. But that's weird because the number of protons is increasing. And the number of electrons are increasing. So you would think, because there's more electrons, they should repel each other and go further away, right? Doesn't that make logical sense? So what must be happening?
Is love getting smaller?
It does get smaller. But logic, at least my logic, initially tells me there's more electrons that are repelling each other. So they want to be further away.
Are attracting the other.
Right. It's actually the protons. The protons are drawing the electrons in. So now, say for, I don't know, silicon. There's only 14 protons in the nucleus. So the electrons are drawn in quite closely. But as you add more protons, the fluorine has now 9. So it can draw those electrons in. All right? Because of the attractive force of the protons. So the atomic radius will shrink because the electrons are being drawn in by the protons. Much like spring breakers to the beach. Okay? They're just being drawn in, so they're being compressed. Even though the West Virginia kids and the South Carolina kids may not like each other, they're going to live with each other because they all like the beach. You know what I'm saying? Going for a little football rivalry there. Guess it didn't work. Okay. So that's how it works. Atomic size, from top to bottom, it increases. From left to right, it decreases. So now, that means the smallest element by atomic size is fluorine. Fluorine is very small. And the largest one you would guess would be francium down here, group 1, or cesium. Those are the small ones, or the large ones, excuse me. Okay. Ionization energy. Please write that down. Ionization energy. Write down the next phrase very carefully. The energy required, or needed, to take an electron from the valence shell. Just to get rid of it. Ionization energy. An ion is a charged particle. So ion means you have a charge, plus or minus. Ionization means to take an electron from your valence shell. So I go into the valence shell, I grab an electron, take it away. How much energy does that take for me to do that? As you ionize, it gets easier as you go down. So it takes less energy to ionize going down the group. So if I want to take an electron away from lithium, so I'm up here, it's pretty simple to take an electron from, pretty difficult I should say, to take an electron away from lithium, and much easier to remove it from, say, cesium that's down here. So it decreases down the group. It's hard to ionize the things on top. It's easy to ionize the things on the bottom. Okay? As you go from...
Is that because they're further away from the positive?
Exactly. They're further away from the protons, so they're not held as tightly. Very good. As you go from left to right, ionization energy increases because their electrons are being held, as you said, closer to the protons. So it takes more energy to get them out of there. Much like the spring breakers, never mind, at the beach, trying to go back to work, you know. I always wanted to know, where do Florida kids go on spring break? Do they really? Oh, I always wonder, because they're already in a warm weather climate, where are you going to go? And to us, it's cold here, right? No one goes to the beach in March. Cold, man. Okay, so ionization. As you go down, it gets easier. As you go across, it gets harder. Make sense? Or at least can you accept it? Yes. Okay? Down, easier. To the right, harder. And that's it for chapter 3, I believe. And we're going to go into chapter 4 right away, because chapter 4 has got some interesting stuff to talk about. Believe it or not, it gets really cool in chapter 4. All right.
So the only thing that's going to be on the exam is chapter 1 through 3?
Yep. Chapter 4 won't be on it. Because that would be rude. But now, be very, very mindful though. Just because I talk about something in chapter 4 doesn't mean I haven't already talked about it in chapter 3. So if it's in chapter 3, it could be on there. If I talk about it in chapter 4, it's still, it's in chapter 3, so it could be on your exam. So don't play that game. I've had people play that game before. You've talked about it in chapter 3 and 4, so it was in chapter 4, so it should be on the exam. And I'm like, whoa, where'd that logic come from? All right, write that down. Octet rule and ions. Octet rule and ions. So now, up until right now, we've only had atoms, and atoms are neutral. Now, we're going to learn why atoms will form ions. Why will an atom form a positive or a negative charge? And that's the octet rule. The octet rule will explain that. So now, atoms that are not noble gases. So noble gases don't have to do this. Atoms that are not noble gases want to look like them. So it's every atom's desire to look more like a noble gas in terms of their electrons. So basically, all atoms want a filled valence shell. All atoms want a filled valence shell, and they'll do that by either losing electrons, gaining electrons, or sharing them with somebody else. They'll either lose electrons, gain electrons, or share them. Chemistry is a business of electrons. Where are the electrons? Where do they want to go? And why do they want to go there? So for example, certain elements, and we'll tell you which ones, love to give electrons away. Certain elements, they can't wait to give an electron away. Certain elements can't wait to take it from them. And other elements don't know what they want to do. They want to give, they want to take, they're kind of schizophrenic. So now, if atoms decide to give and take electrons, so one atom gives the electron away, one atom receives the electron, that will form what's called an ionic bond. I-O-N-I-C. The word ion's in the name. Ionic bond. So to have an ionic bond, you must have ions. Ions are charged particles. Okay? Ions are charged particles. Ions are charged particles. If you have a cation, you have a positively charged particle. If you have an anion, it's not anion, it's anion, you have a negative particle. So ions is like a catch-all phrase for all charged particles. Cations are specific for positive charge. Anions are specific for negative charge. Cations and anions. So now, an ionic bond is the combination of a cation plus an anion. So a cation and an anion come together to make a bond. It's called an ionic bond. Now, covalent bonds occur, first of all, between nonmetals. So write that down. That's a big point. Covalent bonds occur between nonmetals. And they're like the ones they try to steal, but then they feel guilty, so they decide to share. Nonmetals will make covalent bonds. And when we get to covalent bonds, we'll talk a lot more about it. But covalent bonds, if you want to think about it, is a sharing or cooperation between two atoms to share electrons. All right? So, ionic bond. Charged particles, plus and minus, come together to make a bond. Covalent bonds, they share. Two atoms kind of make an agreement to share electrons between one another. I always think of it more as an attempt at theft, but you can think of it as a sharing agreement if you'd like. Now, the octet rule. Remember we circled the 8 valence electrons of argon and neon? That's a big deal. It's a huge deal. Octets. Everybody wants to get there. Now, helium doesn't need an octet. Helium just needs 2. Helium aspires to be a duet. Just 2 electrons, helium's like, I'm good, don't give me any more, I'm happy, I'm stable, I won't react anymore, I'm good, please leave me alone. All the other noble gases want 8. So once they get their 8 valence electrons, they're good, please leave me alone. So now, let's take a look at, let's do neon. Let's take a look at neon. We already know that neon has 2 and 8, right? Ne has 10 electrons. That's 2, 8. And we'll put a square around the valence electron. So neon, 8 electrons. I'm good. Please don't give me any more. I won't let you take any. I'm unreactive. Let's look at the element beside neon, fluorine. Fluorine has 17 electrons. That is 2 and 7. So fluorine only has 7 valence electrons. Pretty simple, right? How many is fluorine away from having a complete octet? It's only 1 away. Now, you desire to be a noble gas. You want to have the same number of electrons that the nobles have, because that makes you almost just like a noble gas. Almost. But you're not quite. Nobles are born into it. You're going to aspire to it. That's not the same thing, right? So what are you going to do? You're going to get one somehow, right? And where are you going to get it from? We'll figure that out later. But the fluorine is somehow going to gain one. Okay. So let's do this real quick. Number of protons in neon is 10. Number of electrons equals 10 for a grand total of 0, right? Overall charge is 0. Make sense? Everybody? So far we're good? Here in fluorine, protons equal 17. Electrons equal -17 for a grand total of 0. Right? That's neutral fluorine. Now, if fluorine somehow gets an electron, let's just say gets it. I don't know how it gets 1 electron. We don't worry about how or where, just it gets one. It acquires it from somewhere. So then, your electron configuration would now go from 2, 7 to 2, 8, wouldn't it? It gets 1 electron. It steals it from somewhere. Or it purchases it, but it actually stole it from somewhere. So it goes from having 7 valence to having 8 valence. Does that make sense? Yeah. It stole it. Flat out took it. So now, this fluorine still has protons equal 17. But now, the electrons don't equal 17, do they? What do they equal? 18. 17. I'm sorry. Where the hell did I get that from? That's 9. 9. Where am I getting that from? Man, I gotta go home and go to bed. That's much better. Holy smokes. 9. Electrons. Sorry about that. -10. So there's 9 protons and 10 electrons. Here there's 9 protons and 9 electrons. So that's going to be 0. Now here we have how many more electrons than protons? 1. We have 1 more electron than proton. Does that make sense? Everybody? Yes. So now you have 1 more negative than you have positive. What's your overall bank account? -1. -1. You have $9 in your account. You write a check for $10. What's your overall balance? -1. You're down $1. Hopefully your bank won't charge you $30 for doing that. Okay? So now you have a charge. You're -1. You have the same electronic configuration as a noble gas, but you're not a noble gas. Okay? So you have to indicate that. So the symbol is not F. The symbol is F negative. That's what you have to write. If the fluorine is no longer an atom, it's an ion. It has the same electrons as neon, but it's not neon. It's still fluorine with a minus charge. Okay? Just because you have the same electrons as neon does not make you neon. In order for fluorine to become neon, it has to gain a proton. And that's really hard to do. It's easier to gain an electron. So it looks just like neon in terms of electrons, but it's not. It's F minus. Okay? The minus charge must be there. Is that okay? Everybody else? Okay. So that's fluorine. I should have 9 there, sorry. 9. 9 electrons. So that's a nonmetal. That's all the way to the right. So it's all the way to the right. So now, fluorine's right here. One more to be like neon, right? So chlorine's right here. So how many more does it need to be like argon? 1. Everybody? 1. Bromine, how many more does it need to be like krypton? 1. Iodine to be xenon? 1. So fluorine needs 1. Chlorine needs 1. Bromine needs 1. Iodine needs 1. All group 17 elements can only ever be neutral or negative 1. They cannot be negative 2. If they were negative 2, they would have 1 too many electrons to look like their corresponding noble gas, right? So they can only ever acquire 1. And that's all they want is 1. Does that make sense? Yes. Everybody? Yes. Let's look at oxygen then. Oxygen is right here. How many valence electrons on oxygen? 6. It's in group 16, so it's got 6. So 6 valence electrons on oxygen. How many more does it need to be like neon? 2 more electrons. If it needs 2 more electrons, what must its charge be if it's an ion? It's gaining 2 negative charges. So what's the charge? Negative 2.
Oh, there's a number. Okay.
Okay? It has 6 valence electrons, wants to have 8. 6 minus 2 is 8, or 2, sorry. 6 minus 8 is 2. 2 negative. So it'll be 2 negative. Now, write this down. Nonmetals will always be negative. Nonmetals will always be negative. Or neutral. They will not be positive. Let's do nitrogen. Nitrogen has 7 electrons. So that's 2 and 5. 5 is its valence electrons. So nitrogen has protons equal 7, electrons equal -7 for a grand total of 0 in the old checking account. So now, that's a 5. Neon has 8. So nitrogen wants to gain how many to look just like neon? 3. Right? So nitrogen will go out of its way to steal 3 electrons. Gain 3 electrons. E minus is the abbreviation for electrons. So it will become 2-8. So now it's 8. So the number of protons equals 7. The electrons now are 2 plus 8 is -10. So the overall charge of nitrogen will be -3 if it's an ion. Because you're $3 in the hole, right? You have $7 in your account. Now you have 10 minus charges against you. So now you've lost your $3 that you owe the bank. And they probably will charge you $30 for doing that. Okay? So now it will be N -3. Make sense?
Yes.
On the periodic table, you can tell this very easily. Neon wants to gain 3 electrons. Nitrogen wants to gain 3 electrons to look like neon. 1, 2, 3, -3. Sulfur wants to gain 2 to look like argon. -1, -2. Sulfur is -2. Iodine, 1 to look like xenon. -1. Phosphorus, 1, 2, 3 to look like argon. Phosphorus can be -3. Do you see how you can read it from the periodic table?
Yes.
Okay. Once you get to group 14, carbon and silicon, carbon doesn't like to form anything. It likes to share. So carbon will not get a charge. But nitrogen, oxygen, fluorine, all the other ones sure will. Silicon won't either. Okay, so let's look at a metal. We got sodium. Sodium has how many electrons? 11. So that's 2, 8, and 1. And that's going to be protons equal 11, electrons equal negative 11 for a grand total of 0. So the charge on a neutral sodium atom is 0. Okay, so you're sodium. You've got one valence electron, and you very much want to be a noble gas in terms of how many electrons you have. So sodium is like, all I got to do is gain 7. And I can be way over here. Yay, let's do it. Until sodium realizes that gaining 7 electrons is hard. You got to really, really try. But then sodium gets smart and says, hey, wait a minute now. Wait a second. Underneath my valence shell is that magical number 8. So if it can just get rid of that 1 somehow, you'll have a filled valence shell, right? Look like neon. So instead of aspiring to be argon, which is a bridge too far, why not just give away an electron and look like neon? Why not, right? Would you rather haul 7 bags of potatoes up the stairs or throw one out the window? Which would you rather do? You'd rather throw it out the window, right? It's easier. Sodium's no exception. So sodium will lose 1. Oops. Loss of 1 electron. So now it'll be 2 and 8. You've lost the 1. The 1 is completely gone. So protons equal 11. Electrons equal negative 10 for a grand total of positive 1. You still have $1 left in your bank account. So now there's a plus 1 charge. So that sodium has the same electrons as neon, but it's not neon. It's sodium. So it's going to be Na plus 1. Okay? Metals, write this down, metals always gain positive charges. Or, yeah, I would say it like that way. Metals always gain positive charges. Or another way to say it is metals always form cations. They never form anions. Metals always gain plus charge. Excuse me. Okay. Metals always gain plus charges. So now let's take a look at sodium. Sodium's right here in the old group 1. So now sodium wants to dump an electron off to look like neon. Lithium will dump an electron off to look like helium. Up there. And potassium will dump off one to look like argon. Rubidium will dump off one to look like xenon. Cesium will dump off one to look like xenon, and so on. All group 1 metals can be plus 1. All group 1 metals, write that down. All group 1 metals can be plus 1 or 0, no charge. Group 1 metals will never be more than plus 1. Group 1 metals can be positive 1. They will never be more than positive 1. They can be 0, but they can't be more than plus 1. Okay? Because it can only dump off 1 electron to look like the corresponding noble.
I just have one question. When you have like a positive 1 or a negative 1, you have that 1 and you just do a positive.
You can just do the negative or the positive symbol for the 1. Okay. But for the 2 or the 3, the number has to be there. Good. All right, so cations form metals form cations. Yeah.
Now, if you're in the middle with the valence here, 4, could you go either way?
No. Well, yes. And actually, you could, but in this class, we just say they don't do either one. They just sit in the middle, and they actually make covalent bonds instead.
Okay.
So, like carbon will make covalent bonds.
Okay.
But in reality, carbon can make anions or cations. It's just hard to do.
Okay.
All right. So now let's look at the one beside sodium. How about magnesium? Magnesium has 12 electrons. Magnesium has 12 electrons. So it's going to be 2, 8, and 2. 12, 8, and 2. So it's going to have 12 protons and 12 electrons for a grand total of 0 charge. Balance the old checkbook there. Everything worked out to be even. Okay, magnesium has 2 valence. So again, magnesium has a choice. Magnesium can haul 6 huge bags of potatoes up the stairs to look like argon, or simply throw off 2 to look like neon. It's better to cast off 2 because it's lower energy. It's easier to throw 2 bags of potatoes out the window than haul 6 up the stairs. So a loss of 2. Lose 2, E minus. So now you'll have 2 and 8 as your electron configuration. Your protons will equal 12. Your electrons will equal negative 10 for a grand total of plus 2. So magnesium can be 0 or plus 2. Excuse me. Okay, so let's look at the group 2 metals. Beryllium, magnesium, calcium, strontium, barium. All of the group 2 metals can be plus 2. Write that down. All group 2 metals can be positive 2 or 0. They cannot be positive 1. They must be positive 2 or 0. So that means you can get calcium metal, which has no charge, or you can find calcium ions, which are plus 2. Okay? I won't go there yet. All right. So, it's all about the octet rule. It's all about the octet rule. Elements want to get there by any means necessary, either by stealing, being stolen from, or sharing. Okay. Everyone's good with that, right? All right, let me get to a learning check. We went over all this stuff. Okay. Now, this learning check, read it carefully. Write the formula and symbol of an ion. So the word ion tells you it's going to be a charge. It's either going to be a cation or an anion with 16 protons and 18 electrons. So you have 16 protons. So what is that called? That's your atomic number, yeah?
Yeah.
And you have 18 electrons. So from that, figure out what atom it is and then figure out the charge. Everybody got it? What's the first thing you look at, do you think? You can look at the electrons, but there's how many protons though? 16. So with the 16, you can go to the periodic table and find out what element you're talking about, right? Because it's the atomic number. So what's the atomic number of 16? Sulfur, S, right? So sulfur has 16 protons. The question says you have 18 electrons. So you have 16 positive, 18 negative. What's your overall charge? If you have $16 in your bank account, you spend 18, how much do you have left? Negative 2. So sulfur, exactly, sulfur is minus 2. Okay? Perfect.
But it said write the formula.
That is the formula, S minus 2.
Oh.
Formula, or I call it symbol, they call it formula. Same idea, same thing. Yeah, I know. I've actually, honestly, I've never heard anyone call it a formula before. I've always heard it called a symbol, but I've never wrote a textbook either, so you know.
There are more examples of this like on the computer, right?
Sorry, that one more time?
There are more examples like this?
Yeah, oh yeah, tons, yeah. In your textbook too, I signed them.
I'm confused why it's -2.
Aha! That's a great question. That's a great question. So let's look at the sulfur first. So 16 protons, right?
Yeah.
So it has to be sulfur. The only element with 16 protons is sulfur. You're good with that? Okay, that's good. That's the hard part. So sulfur. Protons equal 16. Right? So then, if it was normal sulfur, like neutral sulfur, it would have how many electrons? 16. If it was neutral, it would have 16. Very good. 16 equals, electrons equal negative 16 for a grand total of 0. Right? But now the question says this particular sulfur has 18 electrons. So let's just write that down. So now we have protons equal 16, electrons equal negative 18. So you have $16 in your checking account. You write a check for $18. You're overdrawn by how much? 2. So you're minus 2. The bank will say you're negative 2. Right? Exactly. There you go. Negative 2, so it'll be S to the negative 2. Okay? All right, real quick before we go, please don't make any notes. I need to make an announcement. The math quiz, most of you all who did it did really well on it. There's a few people. I'm going to look kind of at the wall now because I don't want to look at anyone, so you can't say that I looked at you and everyone knows you failed the math test. Some people didn't do very well on the math test. It doesn't matter, it doesn't affect your grade, but you may struggle with this course. So I've recommended you to what's called the early response people to try to help you get your grades up. I have emailed you to let you know that I've done this, and they have emailed you to try to get you to come in and talk to them. You haven't responded according to them. They've called you and they've emailed you. Please check your Broward email to see what's going on so you can get a little bit of extra help if you need it. Okay? I was told by my superiors I have to recommend students to this early response. I've done that to try to help you. You have to now respond back to us so we can get you where you need to be. If you don't want to, you don't have to. There's no requirement here, but I would recommend it. So I looked at the wall when I said it, so you can't say I was looking at you. We have an exam next week, so please come prepared. Come early.